Today we're going to do the Unit 10 review over stoichiometry. You'll notice that the railroad tracks, they're listed right here. I've added those in there just to make things go faster on the video, but you'll have to draw them yourself. So, number one, how many moles of A, aluminum, and B, oxygen must be combined to produce 25 moles of aluminum oxide? Well, the first step is to start with the equation. So I have aluminum and oxygen will create aluminum oxide, Al2O3. I need to balance this by adding in my coefficients. So this one is a 4, this one is a 3, and this one's going to be a 2. So now that I know that, I know start with 25 moles of aluminum oxide, Al2O3, and I'm going to convert moles of aluminum oxide to moles of my first substance, which is aluminum. Now that's going to be a 4:2 ratio, and then come out to be 25 times 4 divided by 2 is going to make 50.0 moles of aluminum. And then the next one is going to be, if I have 25 moles of aluminum oxide, again, but instead I'm going to convert moles of aluminum oxide to moles of oxygen. So I need to use the coefficients in this equation. That's going to be a 3 and a 2 because I'm using the coefficients that are listed right here. Okay, so 25 times 3 divided by 2 is going to be 37.5 moles of oxygen. I must emphasize that this review is only for to really just figure out the answers and see how I do these. You're going to have to make sure you do it yourself and you write down what I'm writing down because you'll learn nothing just from watching it. How many moles of water are produced if 13.2 moles of zinc are reacted with nitric acid? I will be given this equation. Zinc plus nitric acid yields zinc nitrate plus ammonium nitrate plus water. So I need to start with 13.2 moles of zinc, and I need to convert moles of zinc to moles of H2O. Now, this is a mole ratio, so I need to use the coefficients in the equation. So the coefficient for H2O is 3, and the coefficient for zinc is 4. So 3.2 times 3 divided by 4 is going to be 9.9 moles of H2O. Okay, now notice that moles of zinc and moles of zinc were here in that we had the exact same unit on the top left and the bottom right, and that is not by accident. That is so that those two units cancel out, and the unit that I'm left with is moles of H2O. Okay, and that's my answer. That's the entire idea of this. So it says how many grams of ammonium nitrate are produced if 5 moles of nitric acid react. So I start with 5.00 moles of nitric acid, what I know and what's given to me, and I'm going to convert moles of nitric acid, HNO3, to moles of ammonium nitrate. Now, ammonium nitrate is NH4NO3. I'm sorry I couldn't fit that in one line. And then I put moles of NH4NH3. Notice I'm always copying the exact same units, and I'm going to put grams of NH4NO3. Okay. I tend to leave these units blank. I like to fill in my units first, and then I like to fill in the numbers after that. So when I have a mole ratio like this one, mole over mole, this is going to come from the equation. So the coefficient for ammonium nitrate is 1, and the coefficient for nitric acid is going to be 10. Okay? And now the coefficient, and now I have G, so that means I need to go to the periodic table to find the mass of nitrogen, 4 hydrogens, another nitrogen, and 3 oxygens. And I end up with 80 grams per 1 mole. So my math works out that I end up with, and this is really cramped, I'm going to put my answer over here on the left, is going to be 40.0 grams of ammonium nitrate. Okay. Now, moving down. Actually, I still need that equation, so I'm going to leave that right there. How many grams of nitric acid are needed to completely react with 250 grams of zinc? So, start with what you know, 250 grams of zinc, and change grams of zinc to moles of zinc. So let's go ahead and fill in the numbers. The molar mass of zinc is 65.4 grams per 1 mole. And then I'm going to take moles of zinc and put it down here. And then I'll put moles of HNO3 on top. Now, so this is a mole ratio, so I need to go to the coefficients in the equation. I have HNO3, its coefficient is 10, and coefficient for zinc is going to be 4. So then I need to put moles of HNO3 to grams of HNO3. Now, the molar mass of nitric acid is 63 grams per mole. I looked that up from the periodic table. I'm not memorizing them and making them up. And I get 602 grams of HNO3. Now, I found that number just by taking 250 multiplied by 1, multiplied by 10, multiplied by 63.5, and then I divide by 65.4 and divide by 2, okay? So I'm multiplying everything that's on top, and I'm dividing every number that's on bottom in my calculator. So I realize that's a lot of marks. Oh, excuse me. I'm going to leave the equation. I'm going to need it one more time. And I'm going to erase this because it's getting messy. 75 grams of zinc, 0.0 grams of zinc nitrate. Wow. Zinc. Couldn't have made it easy, could you, Mr. Russell? And then grams of zinc nitrate to moles of zinc nitrate. And then it's asking for grams of zinc reacted. So I'm going to switch moles of zinc nitrate, NO3, to moles of my zinc. And then change moles of zinc to grams of zinc. Very nice. All right, now I'll put in my numbers from the periodic table. This is going to be 189.4 grams per 1 mole, and then the coefficient for zinc is going to be 4, and the coefficient for zinc nitrate is also 4, and then the molar mass for zinc is 65.4 grams per 1 mole. So my final answer that I end up with, part D, is going to be 25.9 grams of zinc. All right. Good to go. All right. Now it says elemental iron reacts with oxygen to produce iron 3 oxide. How many grams of iron are needed to produce 500 grams of iron 3 oxide? So this is one of those lonely ones that does not have an equation with it, so I got to make it. Now it says the elemental iron, so that's just iron by itself, and it reacts with oxygen. Remember, oxygen's diatomic, and it produces iron 3 oxide, so that's Fe2O3. You remember that from your charges, right? Right? So I need to balance this equation. That means I'm going to need a 4 here, a 3 here, and a 2 here. Once that's squared away, we can now start with our stoichiometry. We'll start with 500 grams of iron oxide, Fe2O3, Fe2O3 and change it to grams of iron oxide, to moles of iron oxide. Anybody notice a pattern? I hope you do. So now the grams to moles, I need to go to the periodic table to find this number, and it is 159.6 grams per 1 mole. And then moles of Fe2O3, moles of my answer that I'm looking for grams of iron, so I'm going to switch it to moles of iron first, and then I'm going to switch moles of iron to grams of iron. All right, and I skipped these boxes. Let's fill those in. The coefficient for iron is going to be 4. The coefficient for iron oxide is going to be 2. And then the molar mass for iron is 55.8. I found that straight from the periodic table. And I take all of those. I take 500 times 4 times 55.8 divided by 159.6 divided by 2. And lickety split, I get 349.6 grams of iron. Awesome. Okay, so number 4. It gives me a combustion equation, and it asks me how many grams of oxygen are needed to burn 275 grams of ethane. So 275 grams of ethane. That's C2H6. I need to convert grams of ethane, C2H6, to moles of ethane, C2H6. Now the molar mass of this is, well, carbon is worth 12 grams per mole, and there's 2 of them, so that's 24 plus 6. 24 plus 6 is 30. So that's 30 grams per 1 mole. And then moles of C2H6 to moles of O2, because I'm looking for grams of oxygen. All right, right here. Whoop, I shouldn't have done that. Looking for grams of oxygen at the top. Now, so the coefficient for oxygen is 7, coefficient for ethane is 2, and then moles of oxygen to grams of oxygen. So the molar mass of oxygen is going to be 32 grams per 1 mole. Okay, so 275 times 7 times 32 divided by 30 divided by 2 is 127 grams of O2. But hey, Mr. Russell, that's not the exact answer because I need to have 3 sig figs, right? I need 3 sig figs here. I have 3 sig figs at the beginning, so my answer should have 3 sig figs. So that means the real answer is 1030 grams of O2 because that has 3 sig figs. Okay, so I would have gotten -1 if I had stopped with the blue answer. So now it says if 94.6 grams of water is produced by the reaction, how many grams of carbon dioxide are also produced? So I'm not going to do that one for you. You guys do it yourself. All right, number 5. If 12.3 moles of iron 2 oxide reacts with 3.2 moles of oxygen, identify the limiting and excess reactants or reagents. This one is going to be almost exactly like one that's going to be on your test, so you better pay attention. I have my equation here. I have iron, oxygen, and iron oxide. Now what I need to do is I need to take the masses of my given reactants. So I have moles of iron 3 oxide, and I have moles of oxygen. So I'm going to put those right here, 12.3 moles of iron 2 oxide, so that's FeO, and then 3.2 moles of oxygen. Okay, and I'm going to convert both of them to the same product, and I only have one product. So convert moles of FeO to moles of Fe2O3. And I'm going to convert moles of oxygen to moles of Fe2O3. Use the coefficients in the equation to figure out these numbers. This is going to be a 2, this is going to be a 4, this is going to be a 2, this is going to be a 1. So the answers to both of those is going to be, this one's going to be 6.15 moles, and then this one is going to be, let's see, 6.4 moles. Okay, so the idea, which one's less, 6.15 or 6.4? That's right, 6.15. So that means that's the limiting reactant, and that is the smallest value. So it asks how many moles of product will be produced. Well, that's going to be 6.15 moles. That's going to be the lesser value, moles of Fe2O3. Okay, and the limiting reactant is going to be FeO. Okay. Now, then it says how many moles of excess reagent remain after this reaction. So what you should do is take 12.3 moles of FeO. That is my limiting reactant. So start with your limiting reactant here. And then I'm going to convert it to moles of FeO, to moles of my excess reactant, O2. So what you'll have to do on your test is just convert limiting to your excess. What this will give you, let's see, hold on, let me put the numbers in here. What this will give you is 3.08 moles of O2 used. Okay, that's helpful because this number is how many moles of FeO were used, and this number is how many moles of oxygen were used. Now that I know that 3.2 moles of oxygen were available, and I used 3.08 of them, these are used, so I end up with 0.12 moles of oxygen left over. Okay, that is your true answer, and that is what is left over. So basically what I'm doing is I'm just figuring out how many are used and then subtracting it from my moles that are available. Now, Mr. Russell, where'd you get this number from? Well, I got it from this number right here. It was already in the problem. Okay. Now I'm going to scroll down and do this limiting reactive problem down here, and I'm going to erase this junk. So it asks me if 70 grams of CH4 reacts with 95 grams of Cl2, how many grams of hydrochloric acid are formed? So I have my equation and I have my starting numbers. I just need to convert them all to one product and then find out which one's less. So start with 70.0 grams of CH4, and then down here start with 95 grams of Cl2. Now this is a limiting reactant problem, but it never explicitly tells me that it's a limiting reactant problem. The way I know is that it gives me the masses of two different reactants. That is a tricky way of going about it, but this is true. If you know the mass of two different reactants, which you commonly do in real life, you need to figure out which one is the limiting reactant. So what I'm going to do is I'm going to take all of these and I'm going to go to the same product. It doesn't matter which product I do. Actually, it does, because I'm going to ask for hydrochloric acid. So I'm going to pick hydrochloric acid for both of them. So I have two different starting points, but I have the same endpoint. So I switch grams to CH4, and this is going to be molar mass is 16 grams for 1 mole CH4, and then change moles of CH4 to moles of my product, HCl, and this is going to be a 4, and this is going to be a 1, and then change moles of HCl, and put its molar mass of HCl is 36.5 grams per 1 mole. Okay, and this final answer is going to come out to 639 grams of HCl. That's a lot of HCl. Now 95 grams of chlorine, I'm going to change grams of chlorine to moles. And molar mass of chlorine is 71.0 grams per mole. And then change moles of Cl2 to moles of HCl. This is going to be a 4-to-1 ratio as well. That means I need to change moles of HCl to grams of HCl and get 36.5 grams per 1 mole. And I get 195 grams of HCl. Nice. Which one's less? 195, right? Okay, so that is the true answer, which means that all of this work, I know it's painful, but you may get the satisfaction of drawing an X through it. I like to draw X's through my excess reactant, so I make sure that I don't go back and use those, because those are bogus and they're not useful. The only one that's useful is the limiting reactant one, which is this one. Okay, the bottom one. All right. One last one. Number 7. I will not do number 7 for you. You'll have to use your own brains for that one. It's going to be the exact same kind of thing, except you're going from grams. You got grams instead. In number 5, you had moles, okay? And you were able to do two steps right there. Well, now you've got grams, so you'll have to do a 4-step process twice. So that one's up to you. Now, number 8 is super easy. What is the percent yield if this reaction is 9 grams of aluminum produces 30 grams of aluminum phosphate? So if I get 30 grams of aluminum phosphate and 9 grams of aluminum right here, I know that I produced an actual 30 grams of aluminum phosphate, and that is my actual yield. Actual yield is 30 grams. Okay, now my theoretical yield is going to be calculated from my Stoich. So I'm going to have to calculate this one. This one is the paper. The theoretical yield is the paper value. The actual yield is the real life one. So how do I calculate it? Well, I need to start with what I know from my reactant. I need to start with 9 grams of aluminum. And then I need to change grams of aluminum to moles of aluminum. Okay. Now there are 27 grams of aluminum per mole. And then I need to change moles of aluminum to moles of aluminum phosphate. Now I'm going to have to write sideways, AlPO4. Now the coefficients for these are going to be 2 and 2, because and so I just need to take moles of aluminum phosphate, AlPO4, and change it to grams of AlPO4. The molar mass of aluminum phosphate is 122.0 grams per mole. All right. So once all that calculation is done, 9 times 2 times 122 divided by 27 divided by 2 should it give us 40.7 grams. Okay, so that is my theoretical, 40.7 grams. So the percent yield is going to be quite easy. All I have to do is take 30.0, divide it by 40.7, multiply it by 100. So when I do that, I end up with 73.7%. There is no unit for this, you just write percent. All right, that's it. Thank y'all for sticking with me this far.